Hi, my name is Chiara Crinò and I am a PhD student at Università degli Studi di Trieste. In this video poster I will talk about the paper I recently wrote in collaboration with Fernando Quevedo and my supervisor Roberto Valando, in which we discussed on the possibilities of construct explicit de Sitter string vacua from anti-D3 branes in the large volume scenario. Let's start with some basic concept. The most studied version of string theory, which is superstring theory, describes a 10-dimensional universe. On the other side, we only observe 4 dimensions. Therefore, we need to assume that these 10 dimensions can be factorized into a 4-dimensional space-time, which is the one we observe, times a 6-dimensional manifold, which is compactified at a very small length scale and whose geometry determines the low-energy physics of the 4-dimensional space. In our work, we only considered compactifications on a Calabi-Yau space, but in general we know that all known compactification procedures produce a huge amount of moduli. The moduli are geometric deformations of the compact 6-dimensional manifold, and we can classify them into complex structure moduli parametrizing the shape of the manifold, Kähler moduli parametrizing its size, and the axiodilaton that for our purposes we will consider to be fixed by the string coupling constant. The problem is that in the 4-dimensional low-energy limit, these geometric deformations correspond to massless scalar fields that are of course unobserved in reality. Therefore, we need to modify our theory so that all these moduli can be stabilized with large enough mass. We already know that this is possible, and in particular, if we turn on fluxes, we can stabilize all the complex structure moduli and the axiodilaton, while if we consider also quantum corrections, we can stabilize the Kähler moduli. Now, without further ingredients, these moduli stabilization techniques allow to stabilize all the moduli at an anti-de Sitter minimum, which is a minimum with negative energy. But we know from cosmological observations that we live in a de Sitter minimum, that is a minimum with positive energy. Therefore, we need to add new ingredients to the theory in order to stabilize all the moduli at a positive energy vacuum. We already know from the original KKLT paper that if we place an anti-D3 brane at the tip of a warp throat in the compact space, under certain conditions, we can get a de Sitter minimum. Starting from this idea, we worked on the following setup. First of all, we placed the anti-D3 brane on top of an orientifold 3-plane at the tip of the warp throat. This is because this specific configuration can be very conveniently described in the low energy limit in terms of an nilpotent Goldstein. Moreover, we worked in the large volume scenario instead of the KKLT1, and we chose to focus on the simplest possible class of models in this frame, which is the class with only 2 Kähler moduli, one of which is much larger than the other, so that the overall volume of the compact space is exponentially large. Finally, we know that in general, the complex structure moduli are stabilized at much larger energies respect to the Kähler moduli. Therefore, we usually consider the two stabilization problems separately. Nonetheless, here we have a warp throat, and we know that at least in principle, the complex structure modulus parameterizing the throat could be stabilized at smaller energies. Therefore, in our work, we considered a 3-moduli problem in which the 2 Kähler moduli and this specific complex structure modulus are stabilized at the same level. Our purpose was to construct an explicit example in this framework, and the main difficulty we had to face is the presence of a lot of constraints that we need to impose in order to have a consistent theory, and that are often in tension one with the other. Here I listed the main ones that regard, of course, the presence of a de Sitter minimum, but also the control over all our approximations, that is the effective field theory, the 4-dimensional low-energy description, and the supergravity description, and the 3-charge cancellation that imposes quite a strong constraint on the value of the product of the fluxes that we need to turn on in order to stabilize the complex structure modulus of the warp throat. Just to make an example of this kind of issues we needed to face, already the first requirement by itself sets a strong constraint on the value of the stabilized moduli that we can accept. Indeed, we can consider only models in which the value of the stabilized moduli is inside the specific range of values which is fixed by this constraint. As we can see from this plot, the width of this range of values is very small for all possible values of the string coupling. Therefore, a lot of possible models are ruled out if we only consider the first constraint. Here I report the main data of the explicit model that in the end we managed to construct and the scalar potential plotted just in terms of the two scalar moduli. I would like to point out that this model satisfies all our requirements. In particular, all moduli are stabilized at the de Sitter minimum. The perturbative expansions are under control, and in general, all consistency conditions are satisfied, though we are usually at the boundary of the region of validity. What can we do next? First of all, we could try to explicitly stabilize all the other complex structure moduli that are present in the model. And it would be in particular interesting to see whether once all the fluxes are explicitly turned on, the D3 charge cancellation condition is still satisfied. Moreover, we could try to extend this work in order to construct more rich and realistic models. This is what I'm working on in these months in collaboration with my supervisor Roberto Valandro and also Michele Cicoli, Veronica Guidetti and Pramod Shukla. Our purpose is to add to these two features that we discussed today also chirality and inflation following the work that was done in this paper. In order to do so, the first step is to find a Calabi-Yau geometry which, at least in principle, can admit these properties. We are focusing for the moment only on toric Calabi-Yau geometries, and here I listed a set of requirements that we need to impose a priori in order to select a suitable geometry. For example, we have the need of at least 4 Kähler moduli. Of course, we should be able to stabilize the moduli in the large volume scenario, and we need a throat with O3 planes if we want to apply the uplift mechanism that I described in this talk. Moreover, there are several other requirements that we need to impose in order to obtain also chirality and inflation. We have observed that these requirements are quite constraining. Therefore, we expect to find only a few possible geometries, among which we will select one, and we will try to build an explicit example similarly to what we have done in this paper. That's all. Thanks for your attention.